of programming GPU enabled codes. And I will discuss in detail about the CUDA programming model. And then I will discuss about the GPU memory organization and third organization and its mapping. These two things are memory organization and third organization and mapping is very much essential to optimize our algorithms on the underlying GPU. Then at last, I will give a demonstration on Kaggle platform and how we can write the Jupyter notebook, our programs on Jupyter notebook, and how to check the environment is ready to run the GPU enabled programs. At last, I will take some question and answer session. So if you have any doubts, you can ask through the chat and I will discuss in live. So the first is a GPU programming model. So I will just show you there are many ways actually to program the underlying GPUs. So you can see that the first one is a standard C++. This is a standard C++ is basically the improved version or enhanced version of a standard C++, which NVIDIA has developed so that they could facilitate the high level programming rather than we are using a specialized libraries for GPU programming, NVIDIA GPUs especially. So they have launched they improved the standard C++ library by adding some advanced features in that, like Lambda, template, and STL, which basically ensure the seamless and intuitive high level development. So for that, what they did, they have given a thrust library, and this thrust library you can study in detail further. But this library basically helps the parallel programming facilities on the GPU. So what we have to do this in this case, we have to include some header files, and in that header files, some predefined functions are provided. By using those predefined functions, we can write the high level program for the underlying GPU. Second one is a most popular is a directive based programming, and this is a very versatile programming model which is widely been adopted in a scientific community. In this, they use OpenACC and OpenMP. OpenACC and OpenMP is a directive based. Meaning is that just like I think in previous session I was saying Om was talking about the pragmas. Similarly, in GPU also we can program the GPU by using those kind of pragmas by passing those pragmas in a particular chunk of the code which we wanted to run on the GPU. So this is a universal method, and this such kind of programs are I used to say it is a universal because it is not architecture dependent. This such kind of programs which is developed by using the directive based programming constructs, so they can directly run on NVIDIA, Intel, or AMD GPUs. Next one is a non-portable kernel-based model. The word is specifically telling us that non-portable means this kind of models, programming models, is used for particular hardware only. Just like CUDA, Compute Unified Device Architecture. This is a one kind of model which is developed by the NVIDIA, and it is an extension of C++. Meaning is that in CUDA, when I will discuss in detail, I will tell you what kind of qualifiers, what kind of functions they have developed, so that the programmer, by using those qualifiers, they can directly interact with the underlying GPU. And this kind of model provides the low level control on the hardware. So first one is the CUDA, and second one is a HIP. HIP is a heterogeneous interface for portability, and HIP is used by the AMD GPUs. Now these days, the people are talking about the portable kernel-based model. The reason is very specific because the architecture of GPUs are changing very rapidly, and new GPUs are coming to the market, and every time we need to change the modify the code according to the architecture is also a very challenging task. So people are talking about that why we cannot develop such a model which can be portable. Obviously, there will be some performance compromise will be there, but it should be portable to any architecture. So in that category, the first is the sickle. This is an Intel sickle we call. Intel sickle is very popular these days to program the GPUs. Meaning is that if I develop my program by using the Intel sickle, then it can run on Intel GPU. It can run on NVIDIA GPUs, and it can run on AMD GPUs with slight modifications. So in that category, the Intel SQL is very popular. Apart from that, OpenCL, Cocos, Raja, these four are very getting popularity gradually. But Alpka, I'm not sure, but it is there. But how much popular, I don't have any idea of this Alpka programming model. Next one is a high level language support. Because these days people are using the GPU device for uh, AL, ML, or application development, and they are very much good in Python, but they are not very good in they are not very good in C or C++, but they are very good in Python, because the Python has a lot of library support is there. But at the same time, this developer wanted to use the underlying GPUs. So in community have provided some high level language support for those GPUs. Just like you can use CuPy, CUDF, CUDA, and Numba. These are the very popular libraries that which is developed by some of the Python communities. Those who are very good in Python and they wanted to use the underlying GPUs, they can use this libraries for underlying utilization of underlying GPUs. Next one is Julia. Julia is also getting very popular these days, and Julia is a language people generally call it a scientific community language. It is much faster than the Python, and this Julia also supports the any of the architecture by just calling its library in the environment while developing the programs. So those libraries are like, if you wanted to use NVIDIA GPUs, so you have to use CUDA.jl. If you are using AMD GPUs, then we have to use AMD.jl. And if you are using Intel GPU, then we have to use Intel.jl. These libraries we have to import in a program, and then Julia will support the underlying GPUs. Now, I will discuss some more detail about the CUDA programming model. Obviously, I will not go the exhaustive way, but simple qualifiers I will discuss, so that at least the first time learners can start using developing their programs. So CUDA, as everybody knows, is a very popular programming model, and just I mentioned that it is a non-portable kernel programming model. It stands for Compute Unified Device Architecture. It is developed by the NVIDIA for their own GPUs. What kind of facility it provides? It provides the ease of integration with C or C++ programming language. Meaning is that suppose you have already one program that runs on CPU, and that is written in C or C++ programming program, and anybody wanted to modify that code, they wanted to use that code to run on the GPU. So by using the CUDA and using the some functions qualifiers, so some chunk of the code can be offloaded to the GPU. So that kind of integration is very much easier in CUDA programming model. Second thing is that because NVIDIA is a very keen to popularize their NVIDIA their GPUs, so they always provide a rich set of libraries and tools, and they always try to understand the challenges from the users, and they modify their models, and they simplify the models, and then again they provide it to the users. So in this way, they provide a rich set of library they have developed, which is widely being used in a scientific user community. So, next thing is it always allow you to focus on solving the complex problem rather than dealing with the low level hardware detail. Because why this statement is here? Thing is that whatever we have an infinite number of problems in the around us, right? But whatever the machine we have, that has a limited resources, and for make our program to optimize for the underlying machine is always a challenge, because architectures keep on changing. That means developer has to understand the hardware, and then they have to understand the problem, and accordingly it has to develop their algorithm, implement the algorithm, so that it could optimize for the underlying hardware. So how we can solve that? So CUDA is allowing that, okay, you have some understanding of hardware, but you no need to understand very low level hardware details. So low level hardware details means there are many things that CUDA has not disclosed. Just like I will tell you that what they are not disclosed in any literature. And thing is that whenever you launch the job on the GPU side, so GPU will automatically schedule the things. So you don't have a control over that, because that scheduling is that intelligent scheduling is implemented in a hardware level. So that is the reason they have mentioned this statement. So developer has to focus on developing the algorithm by little understanding of the hardware. And next is the Nvidia is today is number one company. It has beat the Intel as well, because of its rich ecosystem they have developed. And if you touch any scientific community, you will find that they are using Nvidia's GPUs all around. That is only because of the ecosystem they have developed. They have connected the many communities with them, and they are continuously developing the new thing, modifications they are doing in their architecture and their models or libraries as well. So next important thing is that how the CUDA programming model works on the NVIDIA, or you can say GPU enabled server. In CUDA programming model, every time the CUDA programming is developed in two parts, right? First one is a host part, and second one is a device part. So in a previous session, I already mentioned that host means the CPU and device means the GPU. So whenever we develop any CUDA program, so first of all, that program will run on the host machine, means that program must be executed by the CPU. And wherever the CPU find some kind of instructions, this part is to be offloaded to the GPU. So then it will be offloaded to the GPU part. Sorry for interruption. Next is, that is a flow I will discuss here, how the program, entire CUDA program basically executes in a CPU and GPU. So here you can see that first of all we have written any program. Once a program is written in CUDA, means in C language, the first thing we have to do is first thing we have to do here is that we have to allocate the memory on the host machine. Host machine means CPU and its RAM. So RAM is a memory where first of all we have to allocate the some space, and after that we have to initialize the data over there in a CPU. That is the entire thing is happening on the host machine. After that we have to initialize the space in a GPU, because I already mentioned that GPU also have their own memory, is a dedicated GPUs. So almost equal amount of space is to be created on the GPU memory space. Once the memory space is allocated for to the variables, then the data transfer will happen from host to device memory. means entire data whatever we have initialized in the CPU part, and it is to be transferred to the GPU's memory. Once data will be available on the GPU, only then the kernel launch execution function can start. Otherwise, if data is not available, then how the kernel will understand from where it has to get the data? So that is the reason data is to be copied from host to device memory. After that, the kernel launch function should be executed. Whenever we launch the kernel, it will use the data which is present in its device memory for the computation. And once the computation is done, it will go to the next step and transfer the device data. Whatever the data result it has generated, it will copy the whatever results will be generated, it will also be available in the device memory. The results will not be available on the CPU's memory here. So first of all, what we have to do, we have to transfer the data from the device memory to the host memory. Once the data will be available on the host memory, then we can use the print command and we can see the output and other things whatever you want to verify. After the entire operation is done, we have to release the memory. Memory we are releasing the means we are releasing the memory whatever the memory space we have allocated, reserved. Basically allocation means we are reserving the space for particular kernel in the device memory as well as on the CPU's memory space. The both memory space whatever we have reserved is to be released. Now I will discuss about the function declaration. And this is very important. This is a starting point for CUDA programming. So there are few more qualifiers are there, but because I'm considering as a beginning level, so I'm just focusing on three, which are very important for starting the CUDA programming, and other qualifiers are required for the advanced level programming. So qualifier, the first qualifier is the global qualifier. So what does the global qualifier? It declares the kernel which is called on host and execute on device. So simple meaning is that where so I will just take example here. So you can see that void my kernel. This is a one function. So you can see here this is a function, simple C function, right? And within this function I am writing hello world from GPU. This is my function. Till now this is a CPU function, but just add I here the global keyword or global qualifier in front of it, it becomes the GPU function, right? So this global qualifier is indicating that this function means this my kernel function will be called on the host but execute on the device. That means it will be called on the host and then it will be transferred or offload to the GPU, and when it will be offloaded to the GPU, then GPU will execute this part. After that it will come back again on the host and then it will print. Next qualifier is the device qualifier. So device qualifier is basically tells us that if we are declaring any function with device, here you can see the device qualifier. If we declare any function with device qualifier, that means this function will be called and execute on the device. So be careful whenever I am calling the device means GPU, right? So that means this function, any function which is declared with the device qualifier will be called and execute on the device. Thing is that in my server board there could be a multiple GPUs. So one GPU may call this function and this function can execute on another GPU. This is a one scenario. And second scenario is that if there is only one GPU card, so we can say that if this function will be called on the same GPU and it will be execute on the same GPU, right? So different scenarios it works. Next one is the host qualifier. So host qualifiers means host means the CPU. So whichever function is declared with the host qualifier, You can see here. So this function is not going to execute on the GPU. Such functions will be called and execute on the host machine only. Host machines means this will be executed by the CPU. Next is qualifiers belongs to variable declaration, because as we declare the variables in normal C and standard C and C++ and Python as well. Similarly, CUDA also provides some facility to declare the variables that will be used by the GPU. So here you can see, don't get confused with the device keyword here and the device keyword here. It looks like same, but the declaration is different. So here you can see how here we are declaring the function. Here you can see we are declaring the device function, but here we are declaring the variable, right? So if I use the device qualifier and declare any variable like this, which I have declared here, int variable d underscore var, so these variables will be declared in a global memory space. Global memory space means the GPU space. GPU memory is known as global memory. So in that memory space, this variable will be declared. And important thing is it is accessible from all the threads. The word is global. Global is telling me whatever we are declaring that any variable in a global memory space, then the threads which is being launched on the GPUs, all threads can access this variable with the lifetime of application, right? So till the time application will be alive, that variables will be alive, and all threads within the application to execute those application will be able to access that variable. Similarly, there is another keyword, another qualifier that is called a constant. It declares the variable in a constant memory space. It declares the variable in a constant memory space, and constant, the word is telling is that whatever the value is not going to change throughout the application or throughout the lifetime of application. Those values I can be declared in a constant memory space. So just like that, here I had declared one variable c underscore var, it is 20. So this value, this variable value is not going to change throughout the life of application. And it is also is accessible from all the threads with a lifetime of application. Next qualifier is a shared qualifier. This shared qualifier used to declare the variables in a blocks shared memory. Means shared memories are available in our GPUs, and those shared memories we use to declare these variables. And this shared memory space is only accessible by the third block. So I will discuss third block in coming slides. So the third blocks is used to access the shared memory, and it will be alive till the life of the block. In CUDA, the block means a thread of some group of threads that belongs to particular block. Group of small group of threads is known as thread block, and the application of that thread block will be able to access the shared memory, not all the threads. And lifetime of those threads will be of the lifetime of that thread block. Then there is a restrict keyword, and restrict basically used to used with the pointer to stop the aliasing. So meaning is that suppose you wanted to declare one variable space, some space you have reserved, suppose x is a space, and you don't want that it should be used by, or some other program or some other function should replace the name or change the name, or it should give an other name. You wanted that the name should not be replaced or name should not be referenced. In that scenario, you have to use the restrict keyword. So here you can see that I am using the restrict keyword with the variable a. I am using the restrict keyword with variable b, and I am using the restrict keyword with variable c. So that means they will not be aliased. with any other name. Next qualifier is a managed qualifier. Managed qualifier, basically it declares the variable in a you can say global memory, but this kind of variable which is declared by manage, it can be accessed by the CPU and GPU both, right? In a previous case scenario, in this case you can see I am just considering this case here, just like device d underscore var, you can see this is accessible by the GPU only. This is accessible by the GPU only. It cannot be accessed by a CPU, right? But if we are declaring the variable with the managed qualifier, then this variable can be accessed by CPU and GPU both. Next is a vector type. This is very important in these days because of the complexity of applications and dimensionality of applications related to any object. These vector types are very useful. Uh, First one is a one element vector. This is nothing but a scalar values, and you can use the variables which is used in CUDA. You can use these variables to declare the scalar values. Second one is a two vector element vector. This is also a vector. It is used to store the 2D data, such as two coordinates or 2D vector data. If you want that every object, their two values are associated, so then we have to use this kind of variables. If there is also a three element vector, so typically this is used with the 3D data, and you can say it's RGB color or any 3D vector. Means simple meaning is that if uh, uh, any object has three values are associated or three different parameters are associated with that, so in that scenario you have to use these variables. Similarly for 4 is there. So these four are there, we can use for various applications. And next one is a dim3. It is a special vector type used in CUDA to represent the dimensions in a grid and block configuration. So you can see here with the example, there is a one type dim3 and blocks 1D. I am just passing only one value here. So that means it is indicating that the dimension is only one dimension, right? If but I can pass three values with that because it is a three dimensional. Now I will explain you what is the meaning, what is the importance of this vector elements, these types 1D vector, 2D vector, and 3D vector, and 4 element vector. Just think about you have a some data, and just like person, and each person have a three information you want to keep. Its weight you wanted to store, it is height and age. These three values, these three different parameters are associated with this person. Similarly, next these three values are associated with this person. So how what generally what we do in programming. So because it is a, you can think it is a one vector array, this is a second array, and is a third array and fourth array. So how we can declare? We can declare some variable here, and we can declare that arrays here. So whenever we declare this array, so how the thing is that how it is going to store in the memory. Suppose this belongs to this memory space. Memory is M1, and it is storing this M1 is a memory location, physical memory location, and it keeps the all values of this particular column. Similarly, weight, this is locate in some another and next any memory location in a memory space, and it stores its value, its vector. So on. Variable 3 and variable 4 is also storing a different memory location. Thing is that if my I wanted to access this value of any person x, get, I just say the computer that okay, you get the value, get the information of x1, person is x1. So what will happen? It has to travel different memory locations. Means three times it has to, three memory cycles is required to get the three values for this, and we have to write the logic for that as well. The thing is that the data is not storing in a consecutive. Data associated with this x1 is not storing in consecutive memory location, rather than it is a discrete memory location. It is storing randomly, and to get the data from those random locations, machine has to work more. So another thing is that in a simple terms, it is just an example. So how, what I can do, I can think about why cannot whenever I will call this person x1, and I should get three values in a one memory cycle. So because with this way you are reducing the memory burden on the machine, and you are improving the performance. So in this scenario, such kind of vectors are very helpful. These vectors, this element, three vector element vector, I have taken example here only for three element vector. So here you can see that this int 3, and this is my user, and it has three variables that are associated, and these three variables in memory it will store in a consecutive memory location. So this, I'm just giving a simple example of that, how the memory cycles is impact the performance. So we have, whenever we write our algorithm, we have to take care there should be a less memory cycle should be used for the data transfer. And second example, I will say that suppose you have any image. This is a one box. You can say this is a one image, and we know that each image is made up of pixels, right? So so there are, for each pixel, group of pixels is giving you the image. But what is a pixel here? What the pixel here? I'm just writing pix for short. So there are three things that is attached with that. It has R, it has G, it has B, blue. Three parameters associated with that. But these days there is one more parameter is associated with this one pixel is alpha, right? So that means my object is one pixel of the image, and with that pixel there are four values are associated, four parameter or four values are associated with that, that is RGB and alpha. So you just think which for the computation time, which uh, your vector element or vector type will be useful for this pixel computation. So you can think it of the like this one, four element vector will be useful because it can store four different values in a consecutive memory location. So there is a one more concept and a hardware level that is known as cache line, and cache line size is hardware fixed. Every manufacturer fixed that cache line, and whenever one cache lines travels, that means it brings some chunk of data from cache to the CPU or to the registers. So if your data is traveling in a one cache line, then your operation will be more efficient, and there will be a less cache miss. So this will also improve the performance of the algorithm. So this is a way we have to think and we have to optimize. And thing is that we have to understand which vector type is suitable for my data type or for my the object which I am using. So what kind of advantage they are going to give you? 2D, 3D, and 4D vector types in CUDA. 1D is a scalar, so I'm not focusing on that part. So first is the compact representation it will gives you, and second is it will improve the performance because allow the efficient memory access pattern and better utilization of SIMD capabilities. Simplicity in code, rather than writing the complex code, it will reduce the simplify the code structure and make it very much easier to read and maintain the code base. Next, this vector types helps in optimize mathematical operation because it gives a more straightforward and efficient mathematical calculation. And if you know how the mathematical calculation is behaving, so parallelization is very much easier on the GPU. Flexibility is allow the developer to choose most suitable data type for their application and optimize both memory uses and performance. Next is predefined variables. So here you can see the dim3 and grid dim is a predefined variable that is widely used. I will also use in programming. Block dim, block idx, and thread idx. So these are the predefined variables. Grid dim basically gives the idea about the dimensions of the grid, and it provides a total number of blocks in the grid, and you can find out the dimension in individual in x direction, y direction, and z direction. So this is telling you that how many blocks are available in a particular direction or in a particular dimension. Similarly, the block dim is indicate the dimension of the blocks. So dimension of the block is means number of threads in a block, and the threads also can be arranged in a three directions. So you can find out the how many threads are in which direction by using the block dim dot x dot y and dot z. So blocks and the third idx basically it you can think it about the coordinate system because it is a three-dimension space to find out the actual location of the of any thread in a block or of any block in a grid level. So we need some indexing system. So CUDA also provide those indexing system. This indexing system basically includes the x, y, and z coordinates. So it indicates the unique ID or unique position of the block in the grid or thread in the block. Then next one is the kernel invocation. So as I told you that once your program is ready, so you have to your CUDA kernel is also written, and next is that CUDA kernel is written, but until unless you launch the kernel, it will not identify that I have to offload to the GPU. So that kernel is the launch of that kernel is known as kernel invocation. So here you can see I have just mentioned two example here here. So you have an idea that global qualifier is indicate that this function kernel is to be executed on the GPU. After that, I have defined the dimensions, grid 3, grid dimension, nx, ny, and z, 3 direction. And similarly, dim 3 block dimensions, the number of threads in a block I have declared with this, passing these values. Then how to launch the kernel? You can see these three brackets, you can see angular brackets here, you can see this is a kernel, the same name, the kernel, what are the name of my kernel I have given, the same I will use here. But when I will use this triple angular brackets, and within this triple angle brackets, I have to pass the grid dimension and block dimension. Only then this kernel function will be launched based on the values we have provided at here and here, grid dim and block dim. But here I am not passing any input. But thing is that in some time we need to pass the input to the kernel. So how to pass that kernel? It totally depends on how you have written your kernel. So here you can see that I have written my kernel here as a global keyword I have mentioned. When I am written this kernel, so I am just passing one input, output, and int size. Three meta parameters I am passing. But here I have not passed anything. You can see I have not passed anything here. But in this kernel I am passing three parameters to that, and the same dim 3 and grid dim 3 block dim parameters I'm not changing here. So here I have to okay, my kernel name is my kernel, so I have written only my kernel here. It should be my kernel, same name which I have used to define my kernel, same kernel name should be used. With that, I have to use three angular brackets, and within these brackets, I have to pass the grid dimension and block dimensions. After that, you can see here, I have to pass these three inputs because my kernel, when I define my kernel, there are three parameters I have passed. So same three parameters I have to pass while launching the kernel. Only then your kernel function will execute, otherwise it will throw the error. So apart from these two, grid dimension and block dimension, there are other two parameters you can pass, that shared memory size you can fix, and a stream I'm not going to discuss, this is a bit advanced topic. But shared memory size basically is the size of memory in bytes. So whenever you are launching any block, so you can specify how much of the register space they can use, or you can say that how much of the shared memory space they can use. Now, host and device function memory. So you know that my entire compute server has two things. CPU means host, device means GPU. So I am going to allocate some space on the host machine. So I have to use malloc. But if I wanted to allocate the space on the GPU device, then I have to use the CUDA malloc. Similarly, I have to use mem copy, and here I have to use CUDA mem copy. So you can have to take care of the syntax in CUDA case. There's a M is capital everywhere, and in free, yeah, F is CUDA free, F is capital. So this syntax are very important. Most of the time while typing or while using these functions, we use this kind of mistakes, and because of that, it gives a lot of error in troubleshoot, and it creates some challenge in troubleshooting. Next is the atomic function. So atomic functions, if you are coming from background of C++ programming, so you must have an idea of what is atomic programming. So atomic programming in general sense is very helpful whenever I am using the global memory and shared memory space. Means whenever multiple threads is trying to access the same memory space, and it always creates the race condition. So to avoid those race conditions, so we have to use the atomic functions, and there are different kind of functions are available. Broadly, you can categorize in bitwise function and arithmetic functions. And but thing is that whenever we are applying a lot of atomic functions, so it will your parallelization effect will be loose. So we can lose the parallelization effect. So we have to use this atomic functions very carefully in a parallel programming domain. So I have just provided the entire list of the atomic functions that is available in CUDA, and developers can use these functions as per their requirement of algorithm development. So or implementation of any algorithm. Next one is the synchronization function. Synchronization function is also because we are going to launch the number of threads in a parallel programming. So the synchronization is very much required to manage the threads, and this synchronization functions basically provide a synchronization at three different levels: thread level, block level, and device level. So ultimately everything is a thread. So we'll say what is the meaning of thread level. So sync thread level basically indicating that it is a, you can see here this function underscore underscore sync thread. So this function is basically belongs to the block level synchronization. So basically each block in a CUDA has some small group of threads. So this function basically helps to synchronize, provide a synchronization within a block. And second is the warp level synchronization. So the warp level synchronization is provide the synchronization within a warp, and we know that within a warp there each warp has 32 threads, right? So I will tell you what. Suppose you have here 128 threads in a block, one block. So whenever this block will be launched on the GPU, so that will be mapped on any SM. So basically what will happen, this will be divided into automatically the chunk of 32, 32, 32, and 32. So meaning is that these are warp schedulers are working inside the hardware level. So they automatically divide this threads within a block into chunk of 32. So this is also a threads. So to set up to synchronize the threads within this warp, so we have to use underscore underscore sync warp function for the synchronization. Next is a CUDA device synchronization. So this is a device level synchronization, and it means device means entire GPU is talking about. So we want to synchronize the all the threads across the entire GPU card. In that scenario, we have to use this kind of synchronization function, and this synchronization will always happen before the data is transferred to the host machine. And next synchronization is a CUDA event synchronization. So this synchronization is basically the event level. If you are specifying any event or if you are specifying any condition, so and you want that until that condition is met or until that condition occurs, the synchronization should not be done. Your synchronization should be done. So that kind of means synchronization can be achieved with the help of CUDA event synchronization. But thing is that both are somewhere helping in avoiding the race condition. But what is the difference in these two atomic function operations and synchronization operations or synchronization functions? So thing is that atomic operation always works on a individual memory access, because it is always targeting the variable, and variable is always stored in some of the memory space, and that memory space has a unique address. So that is the reason atomic operations are uh, always associated with the specific memory address, and ensure that atomic read, modify, and write to the particular memory location. If one third has access that got the access of that memory location, then other thread cannot you access or read or write or modify that memory location until the previous thread is released that. So similarly, the synchronization is basically the thread of management. It operates on block level, warp level, and even device level, ensure all the threads reach a certain execution point. If I talk about the scope of this atomic operation, so atomic operation scope is limited to the memory location, but synchronization is scope is in all level, warp level, block level, and device level. Third execution aspect, if we see the no effect on third execution order, because it's not going to impact the order of the threads execution, because there's a huge number of threads, and atomic operation doesn't mind which order threads are going to execute, because it is binded with the memory location. But synchronization basically synchronize the thread execution flow. So likewise, you can see the memory access, use cases and performance. I'm just leaving it for your reading purpose later on. Now, the CUDA also provides some device query functions, and these functions are very, very helpful. There are two ways. If you want to gain the understanding of the any new device, underlying device which is connected with the machine, either you have to read the white paper or its manual, whatever is published by the OEM, or you can use the device query function that is mentioned here to gain the sufficient understanding or sufficient information about the device. So CUDA has provided some such kind of device query functions, and you can use these functions to know about the capability of the GPU. So I will just take not I will not discuss all, but I will just give you small one or two to explain you. Like I will take here this one, CU device get attribute, and what kind of attribute I am passing here. You can see here I am passing that I wanted to know, basically with attribute I am passing here is CU device attribute maximum thread per block. So I wanted to know that underlying GPU. I have one GPU, and I wanted to know how many maximum threads per block that particular GPU supports. That information I wanted to know. So I can use this function, and it will give me the maximum number of threads per block information, and it will print it. You can print it on your on terminal. Next is I wanted to know that how many multiprocessor count. Multiprocessor count is nothing but a SM count, right? Streaming multiprocessors in a particular GPU. That I discussed in a previous session that in A100 card has 108 SM. So I wanted to know that how many SMs are present in my underlying GPU. So you can pass this function and print this value. It will return the maximum number of SMs on the device. I will show you this in a hands-on session as well. So likewise, you can get almost many informations is available. Just like you can find that maximum threads per multiprocessor. You can find the maximum registers per block allocated. You can find this information. You can find the maximum size of shared memory per block. All these things information we can find easily by passing this info by passing this device query function in a program. So I have a big list. This list, if you use, if you try, so it will be helpful for you to help help you like in learning the programming and gaining the knowledge about the underlying device. Next is the CUDA error handling functions. The CUDA also provides some error handling codes. So these codes are very much helpful for the developer to find the exact cause of error that is occurring while they are trying to execute the code on the GPU. Right. So suppose that like you are using the this error code CUDA success. Okay, you have written somewhere in your program, you have passed this error code. So whenever you get this, that particular chunk or entire program, wherever you have passed that, it will indicate that no error. It's CUDA success basically indicating that it has no error and operation has been completed successfully. Similarly, if you are passing this CUDA error memory allocation, so in if any error related to this memory allocation comes, then it will indicate that memory allocation failed. Right. So there are many things, just like CUDA error launch kernel failure. You are trying to launch the kernel, but kernel is not launching, it is getting failed. So this will indicate you that launching of the kernel has failed. So this is a very helpful for a developer point of view, those who are developing the code and they wanted to check that where the error or where the cause they wanted to identify the what is the root cause of the problem. So by using this error code, they can get a lot of useful information to debug their applications or debug their algorithms. So I have provided the list. Learners can use this error code. Now there is a device specific flags. So there are some device specific flags like -G. While we because my program, whatever the program we are writing, that is a high level language. So we have to compile it to the low level language, means machine codes. So we have to use NVCC compiler. I will show you. But with the help while compiling the program, we have to pass some flags. So one of the flag is that -G. So this is basically generate the information for the device code. So whenever you pass this -G flag, so it will give you the debug information for your code. Next flag is the max register count with number. If you wanted to limit the number of registers per thread, so you can specify the number, and that number of threads, that number of registers will be used per threads. So this is a one of the way generally we don't do. But if you are advanced programmer and you have a complete hold and complete understanding of your algorithm and the variable like whatever the threads you are launching, and you know that how many of the threads is going to, how many of the registers is required for a particular thread to execute the operation successfully, only then this function should be used. Otherwise we don't use these functions. Second flag is a use fast math. So this flag basically, just like Om has shown you some flags. Similarly, this is a flag. It just tells that, indicate that use the some optimized mathematic libraries or optimized mathematic functions. This optimization somehow give you the may give you the performance, but sometimes it reduce the precision. So that kind of negotiation we have to take care. That is a, there's a totally depends on the um, developer intelligence, how far he consider that precision is okay. And if you find that precision is not okay, they need more precision and they cannot compromise with the precision, then they have not to use this flag. Next is the optimization flag. So in optimization flag, you can see here, just O indicates the optimization, and number is representing the levels of the optimization, and this flags only simple level, and O3 is the highest level of the optimization. But keep remember, it is not always guarantee you the highest level optimization will give you the better performance. It is never happen. Some cases it will give you, and some cases it even worse the performance. And it depends on the complexity of the algorithm, right? It depends, totally depends on the complexity of the algorithm. It is not a hardware problem. It is a depends on the way we have written the algorithm. Next is that, next flag is x ptx as, and is the option. So in, if you are working in a cpu, then this flag will work directly. But when we wanted to optimize our code on underlying gpu, nvidia gpus, so we have to use this flag, because nvidia use ptx assembler, and this options is basically is nothing but a o1, o0, o1, o2 and o3 options you have to pass here. The next flag is fmat, and if any programmer or any developer has used this fmat functions in their program, and they wanted to compile their algorithm with that functions only, so they can enable and disable this fmat functions using equal, by writing it equal to enable or disable, means true or false. They can write fmat is equal to true, then it will be enable. Fmat equal to false, then it will be disable. So important thing I wanted to show you, this note is very important. So how do we compile? Suppose you are compiling your any code with this way. NVCC NVCC is NVIDIA C++ compiler, and hyphen O3 is a optimization, is the highest level optimization you can see here, and .cu is indicating the CUDA, and hyphen o the simple output, and this is a file name, is my output file name. If you compile this your CUDA program with this flag, hyphen o3 flag, so because I have not used the xptx flag here, that means whatever output will come, it will not show you any error, it will compile your code successfully. But main problem it is that that code will be optimized for the cpu only, but you are expecting you are doing the optimization for gpu, which will not happen. To optimize your code gpu, the correct method is this. You can see this line. The correct way of optimization is this. You have to nvcc hyphen x ptx as hyphen o3 space hyphen v file name dot c and hyphen o file name. So this is a correct way to optimize the CUDA code for the gpu. Now I will discuss about the memory organization. So in any GPU, the following memories are available. You can see that the global memory, a shared memory, local memory, constant memory, text memory, and registers memory. These memories are available in any GPU. Then you can see that the fastest to slowest and highest to lowest capacity. So register means register file is always the fastest memory, and after that there is a shared memory which is the fastest, constant memory, texture memory, local memory, and the slowest memory is a global memory. Similarly, if you see the capacity, in terms of capacity, it is a reverse. Global memory capacity is always very high, and register capacity is always very less because register files is very much close to the uh, execution cores. So these are descriptions I have mentioned. You can participants can read about it. I will just going to the important part of organization of threads in CUDA. So there are two things. First thing is that there's a thread. Thread is a software entity. Is a software entity, and core. Core is a hardware entity. The two things are always available. And what we have to do, the software things should be mapped on the hardware properly. Only then you will get the optimized performance. You can get the result in serial code, sequential program. You will get the correct answers. That's fine, but what we are doing when when we have a very powerful hardware and we are working on the parallel programming, so mapping of the software entity on the hardware is very important. So every core, this core is people generally in many article they given a different names to that. Some people call it CUDA core, some people call it scalar core, streaming process, scalar processor, streaming processor, single processor, but I will use the word here streaming processor. I will use the word stream or streaming processor. In short, I'm writing, right? So every thread, software entity, the finest software element, finest software program, or I can say the code which is going to execute is the thread. So this thread is to be mapped on this scale streaming processor. When we are combining the large number of threads here, this large number of threads is known as the thread block, and this thread block will map on the SM is what? Streaming multiprocessor. And streaming multiprocessor means it is a group of streaming processors. You can see all are the group of streaming processors. This all are the streaming processors are here. So streaming processors and group of streaming processors is known as streaming multiprocessors. This is a hardware entity name which I have discussed in a previous session. After that, we have to launch a large number of thread blocks. Large number of thread block is to be mapped on the entire GPU. Means suppose I have mentioned that A100 card what I was using, it has 108 SM. It has 108 SMs I have. So fully utilize this all SMs, then I have to use the same 108 number of thread blocks. I have to map on the SM. Only then I can say I have mapped all the threads on all the streaming processes that are available in a underlying SMs. So this is the most important part for the optimization. So because we have thousands of cores are available, we have to carefully figure out that which is the uh, optimal mapping of the software entities on the hardware entities. So thing is that in a software level, there are three things. We start with grid. Grid is a group of blocks, and block is a group of threads. So you can see in a software entity, kernel always executes as a grid, and within a grid there is a blocks, and within a blocks there is a thread. So ultimate the executive unit is the threads. in nvidia, how this blocks and grid, we can say blocks and threads are arranged. So they can arranged in a three dimensions: 1D, 2D, and 3D. So if I talk about the grid dimension, so grid dimension is nothing but a block structure in a grid. So these blocks, you can see that there's a grid means the entire gpu. And within, how I can launch within that grid, the blocks can be one dimension. You can see all blocks in one dimension. These blocks can be in two dimension. These blocks can be in three dimension and this dimension, right? Similarly, within a block, threads also can be launched in one dimension, two dimension, or three dimension. So here you can see this a green box is representing the one block. You can see is a block b0, b1, b2. So green box is representing the block, and within that block there is a group of threads, and these threads are also can be arranged in one dimension, two dimension, and three dimension. You can see here, right? So this is the most important part we have to understand when we have to map the our application on the gpu. Now, how to identify the dimensions of the block and dimension of the threads. So we have predefined variables which I have already discussed. That is a grid dim.x. It basically indicates the number of blocks in x direction within a grid. Grid dim.y is the number of blocks in y direction. Grid dim.z. So basically it is indicating the dimensions, number of blocks in each dimension. After that, each block has some unique number. So because each this block has some unique position, this block has some unique position, and this block has some unique position. So this unique position means it is a coordinate. We need to identify the coordinate of those that block. So that is the reason we have to use the block idx x direction, block idx dot y direction, block idx dot x. So idx is basically indicating the index of that block in z direction, y direction, and x direction. So this is a coordinate system. You will get the three coordinate values of that particular block. Within a block there are arrangement of threads. So block dim.x is also predefined variables. So number of threads in x direction, block dim.y and block dim.z. So it also indicates basically the number of threads in x direction, y direction, and z direction. Similarly, that we have done in block idx. So each thread also have their unique position in a block, within a block, so that we can identify with the help of this thread idx variable. So you just view here how is a 1D grid, 1D block. So all blocks are arranged in x direction and threads are also arranged in x direction. Here you can see there are three blocks that is in all are arranged in x direction, and within a block all threads are arranged in x direction. And another important point to be noted that within a block each thread has their id, thread index is same within a block. Similarly, suppose there is a one day grid, 1D block, and I wanted to calculate that the unique ID, unique global thread ID of this one, because you can see this coordinate is showing same within a this block. This coordinate is same, and this coordinate is same. But how the machine will understand that which operation it is performing, right? So I will show you the example first. This one, suppose I have a one array. You can see array, and each array has element 1 to 12, and I want that I have written a one small code, kernel code, and I wanted that and each uh, element to perform this operation means to square, and expected output is this 1 4 9 16 25 and 36, like so on, right? So first I will see that I can arrange. These are the possible combinations. What I am showing in a CUDA programming model, these are the possible combinations. I can launch one third block. I can launch all one block here, and within this block, one block, and I can launch 12 threads. There's a one way of doing it. So one block I am launching, and suppose my GPU has I'm just SMs I'm writing. My GPU has 5 SMs. Suppose my GPU has 5 number SMs. So you can understand simply is a 5 SMs are there. So I have launched only one block. So means one block will be launched on one SM only, and this SM will execute my 12 threads, and remaining 4 SMs will be idle. They will not do any work. If the same operation, if I break in this manner, two thread blocks, means there will be a two thread blocks, and each thread block is able to execute 6 threads. I divided that. So these two threads simultaneously, it will go to this will go to this SM, and this will go to this SM. So simultaneously, out of 5, 2 SMs will come into the action, right? Now, what I do, I take this combination, 3 blocks. I have taken 3 blocks here. I will draw here 3 blocks so that I have taken 3 blocks, and each block has a 4 threads. So you can see that I am not changing the thread count because the element size and thread element size is equal. So these 12 threads has divided into the 3 thread blocks, and this thread blocks is going to map on each SM. So likewise, all 3 SMs will execute simultaneously. So this is a way the how the means we have to divide the entire number of elements in terms of blocks. I have just taken a small example, but in case of GPU, you need a very lakhs of size of array is required for the effective utilization of the GPU by use, because it works on the concept of latency hiding. So it can hide the memory latency, it can hide the computation latency as well. So similarly, you can find out that these 3 cases, 4, 6, and 12, how it can be mapped. Now, we will discuss why we need to calculate the block ID, global thread block ID, why we need to calculate. It is important to be calculated. We'll see here. Suppose I have a 20 elements. My array size is 20 elements. So this is, I'm dividing into the block 1, and suppose this is my block 2. This is third block. So I will simply say is a third block. I will TB and TB. So whenever I am dividing my 20 elements in a two third blocks, so thread IDs will be T0 to T9, and for TB2 also thread ID will be T0 to T9. When, and this will be mapped on two SMs as I mentioned. It is going to map on two different SMs. Suppose it is SM0, and it is going to map on SM1. So it is a TB is a software block, and SM is a your physical block, main execution blocks. So when it is going to map, and they are executing this function of a square function, and after the result is done, and if you wanted to see the output of T0, you want to say okay, print the what is the output of T0, then you may get either 1 or 121, right? So you are not able to find out which one is correct. It may print because it depends on which thread has executed later, because it is going to change the variable location, and it will print you like that. This t0 is print, may print 1 if it is access quickly, this third has access quickly, and it may print quickly if this one is access first than this one. So but is not giving you the proper answer. So what is the solution you have to do? The solution is that we have to calculate the, or we have to provide the unique thread IDs to each block. I have launched two block in the previous case, but in this case what I have did, I have computed the unique ID to each thread of each block. So here you can see, if you execute the same function and if you ask that okay, print the output of t0, it will print 1. If you say the print the output of t10, it will print 101. So that is a need of calculating the global thread ID. It is very very important. If you are missing that, your maybe your program may be right, but because of small mistake of calculation of global thread ID, you may get the wrong results, but your program may be right. So I will show you that how to calculate the global thread ID. In a global thread ID, how you can calculate, one option I will leave on you, is a universal formula to calculate the global thread ID. It supports for 1D, 2D and 3D. So here you can see that to calculate the global thread ID, you have to calculate the global block ID first, and this calculation I am leaving how you can calculate, but I have already indicating here how you can do that. um, I'm just giving the hint here, but I'm leaving this calculation to the participant so that they can understand how it has been calculated. Second option is the threads per block, and next one is the how they can calculate is that the thread uh, ID in x direction, it should be multiplied in block dimension in x direction, block dimension in y direction, plus thread idx multiplied by block dimension in x direction, and finally thread idx. All these three parameters they have to use here, and the same kind of parameter you can use in calculation of global thread id for calculating the global thread id. So I will just okay, take. Okay, so there is a small practice how you can calculate that. Suppose I wanted to this is my blocks are arranged in 3 dimension, and within a block I have given the coordinate value of each block. So I am just doing the calculation here how you can calculate the global block ID, but you can write your formula, a formula you can write in your own way. Suppose I wanted to calculate the block ID of this block, just I mentioned. So I have taken out this thing to here, and then I, because I am interested in this. So how you can find out? So first I have to find out what is the index value in z direction. So z direction it is belongs to 1. So I will write here 1, and then I will multiply by the dimensions. How many blocks are there in this plane? In this particular plane, how many blocks are there? So x direction it is a 4, and y direction it is a 2. So it is multiplied by 4 into 2, and then I have to make a plus 1. Then I will go to the y direction. I am coming from z direction, y direction and x direction. So in y direction I will see now it is belongs to my y direction, so this value is 1. So you can see here this value is 1, this belongs to this value. I wanted to find out the value for this block. So this value, y value of y third index is 1, so it is 1. And then at this position how many blocks are there? There are 4 blocks, so it will be multiplied by the dimension of uh, grid grid dimension of in x direction. So it will be multiplied by 4, and plus what is the exact value of third index value of this block, that is 0. So when I compute this you will get the value 12. So you can calculate that it is a 0, it is a 1, it is 2, it is 3, and it is 4, it is 5, it is 6, it is 7. At downside, you can say it is a 8, it is a 9, it is 10, it is 11. So it is finally 12. So is the final global block ID I have calculated. So you see same formula you can apply here, and you can do the calculations for your practice. Now I will jump to some hands-on session here. So first program you can see here is the Hello World program. So you can, I have already explained you that global qualifier you have to use here, CUDA hello program, and this is a kernel function. But this kernel function is to be written in a main function, is a main function. Within that main function I am using calling or launching this kernel. Here you can see that I am launching one block, B is one block, and this one is indicating one third value. So one block, one third. So it is always print only one time hello world from GPU. Next, you can see that this is a program for C program, and this is a CUDA program. It's a CPU program. You can say this is a CPU program. I will write here. This is a CPU program, and this is a GPU program. You can see that the difference between CPU and GPU, right? Now I will just uh, take you here. These programs are here for practice, but I will indicate you that. So you can refer this my practice code that is available. A number of CUDA programs are available at my GitHub, and similarly my presentations are available here. So you can view the presentations, different presentations, and maybe some programs I will also add in this site. So first of all, I will go here. Uh, just just a minute. I will just show you. I think, please anybody confirm me that my GitHub page is visible to everybody.
Yes, sir.
Okay, thank you. So here you can see the CUDA codes are available on GitHub link. So all programs are available here. So I have just arranged in an order so that you can start learning from device info to higher level, and the same on the same GitHub page I will upload few more advanced programs. So all shared memory, matrix multiplication issue with shared memory, global memory, vector add, all are available here, including some unified memory concepts. So you can use this one. And the second thing is that okay, this page is also available here. So here you can visit all the slides that is available, and some programs I'm going to add here, advanced programs, CUDA practice program, and threat fencing programs. You can find it here. Now I will just, because of the short of time, so I will jump directly on the Kaggle notebook. If anybody, I think nowadays everybody has a Kaggle account. Otherwise, if you don't have a Kaggle account, you can create a login in the Kaggle account, and after login into the Kaggle account, you can go to the setting, then you can go for the accelerator. So if you are a first time you are using that Kaggle account, then it need a phone verification. It will ask you for the phone verification before using the GPUs. So after the phone verification, this accelerator tab will be added in the setting tab, and here you can see that there are some GPUs are available along with some TPU, VM TPUs are available. So right now what I am doing, I am selecting the GPU T4, right? So it will turn on the GPU. Now I will just run this command exclamatory sign and which NVCC. So just to check that whether my NVCC compiler is present or not. If it will show me the NVCC binaries is present, so my environment is ready. Okay, so you can see that it is showing me here that opt conda bin NVCC. So binaries are ready. So I can use this platform directly. So now you can see that I have written percent write file is a command for the Jupyter notebook. And after that, this is a name device info because I wanted to get the device info. So I just given the name and .cu is the extension name. After that, this is a very simple program of getting the device information, right? So this is the information. Uh, just I have discussed with you. The some functions are available in CUDA. So these functions I wanted to know about it for underlying device. So that is the reason I have taken this function. If you want any, you can add here. So what I will do, I will first of all I will just save this file because, and whenever you save this file it will show you the right thing. If I do once again it will show me the overwriting, so that is fine. Now you can see here is that I am compiling exclamatory sign NVCC device info is my file name, dot o my output file name should be device info. So what I am doing here, I will just compile it. Okay, it has not thrown any error. That means program is compiled successfully. After that, I will execute this information. Then I will see what information it gives to me. Here you can see that it is telling me that there are two device supporting devices detected. And you can check that here accelerator I have selected GPUs T4 and into 2. That means there are two T4 GPUs are available currently in my environment. So that is detected by them. So it is telling the device 0 and device 1, Tesla 4, Tesla T4 and T4. After that, it is giving you some information. Whatever I have asked in my device info program, it has given to me. Okay, because of the time constraint, I am not able to explain everything. But important thing I will show you that in this device, it is telling me that multiprocessor count. There are 40 SMs are available, right? What I will do now, I will just do the sum. I will not going to change any program, but I am going to change my GPU here. Simply I will change my GPU, and after that I will run this again, all programs. Whenever you change, the session will be broken, so you have to run each and every shell again. Okay, it is run. Now I will compile it. After the compilation, we can run here. So now you can see that my same program, I have not done any changes in my program, and it is now detecting that it is a one device supporting CUDA, and it is a Tesla PE PC 16 GB, and it is major version, minor version, and it is telling that this has how many core, 56 SMs are available. So likewise, you can run your programs and test the programs, and I have shown you the GitHub link, so you can run. If you face any difficulty in understanding, you can reach to the coordinator and they can reach us, so we can help you to sort out your problems if in case you face any problem. But ultimately, my experience is that nobody face any problem if they know that how to execute the programs. So this is for this session.
Dear participants, if you have any questions, you can just put them in the chat box.
The first thing I would like to tell you here that the CUDA is understanding CUDA takes some time, right? So it is not like that. It's not like CPU because suddenly you have to throw lots of threads are there and how to parallelize because its nature is totally fully parallelized. So sometimes it takes some understanding, but it is once you understand the basic thing, means mapping of software on the hardware, then it will be easier.
Okay, sir. Yeah. Thank you very much, sir. It's my privilege to offer you the end remarks on the session delivered by you, sir. So today the session you took on CUDA programming is very uh, inspiring. Your experience and then your practical expertise made us to think how this CUDA program can be done for parallelization. And this knowledge differently harnessed as to uh, apply in parallel environments, sir. So thank you very much for your quality session and then sharing the good knowledge on parallel programming, particularly CUDA programming, sir. I sincerely thank you on behalf of the organizing committee, the Department of IT, Chaitanya Bharati Institute of Technology, even on behalf of the our participants. I once again extend my sincere gratitude to you, sir, for your valuable time and then session. So let us all apply these learnings in our day-to-day academics and then research. SAR is very open and he also has his own website where we can see and then learn more on this parallel programming. And he generously shared as the uh, GitHub repository, and that I'll also try to share with you all. And that will be really useful for us initially to practice and then learn and then apply. See, as you said, sir, it takes time. We do understand, but your session made us to think and then take up this job easily. So once again, thank you very much, sir, for your valuable time and then session.
Thank you, Dr. Ramakrishna ji. And one more thing is that in January, I think NPTEL course is going to launch on the same. So participants can learn from there itself. So they have there I have almost more detailed explanations are there. So participant, if they are interested to enhance their CUDA programming skills, they can join that